Hello physicists and welcome. In this session we'll be looking at series circuits, parallel circuits, and the power in an electrical circuit. Let's get started. Hey, so first a quick review of a series and a parallel circuit. On the left we have a series circuit. Notice there's only one path for the current to pass from one side of the energy source, our battery, through our resistors and back to the battery. In this, in a parallel path, we end up having a branch in there. We can think of it as being parallel lines or parallel paths. So the current that leaves the battery has a choice. If we want to give it human emotions, it has a choice to pass through this light bulb, the lower light bulb, or the upper light bulb. Let's provide some details. Hey, as mentioned before, in a series circuit, there's only one path. Let me see if this thing is coming up here. Only one path for the current to pass through. It leaves the positive end of the battery. See that up here. Through the light bulb, through the light bulb, through the light bulb, or whatever the resistor is, through our switch, and then back to the negative end of the battery. Whatever current that passes the current, remember, letter I we use for current, passing through resistor 1 is equal to the current passing through resistor 2 is the current passing through resistor 3. So a series circuit has only one path for the current, so the current is the same at any point in the circuit. But something else in a current circuit is, or in a series circuit, is that the total resistance is the sum of all the individual resistances. If I'm a charge, I got to fight through one resistor, I got to fight through another resistor, I got to fight through a third resistor. Often I've been giving the analogies in class of going through one door, then the next door, then the next door to get out of the room. It's more difficult if I have to open and close consecutive doors to get out of the room. Okay, so adding resistors in a circuit is like adding pinches in a hose or doors to getting out of a room. The greater the number of pinches or the number of resistors or the number of door, the greater resistance to current. Hey, so another important thing is that our voltage drop. Okay, our voltage drop, or another way of saying it, is our voltage gain. And remember, our voltage gain is where we get our energy. Voltage gain in a circuit equals our voltage drop. In this circuit, we can see that our battery is providing 3 volts of voltage gain, and our charges have to drop, in this case, drop 1 volt, drop another volt, and finally another volt. So we have 3 volts of voltage drop. We have 3 volts of voltage gain. It's this one is actually known as Kirchhoff's law. Kirchhoff's second law is that when we go around a complete circuit, we start at a 0 voltage, we go up to 3 volts, we drop 1, drop 2, drop 3 volts across whatever number of resistors we have. So the voltage drop is the difference in voltage across an electrical device that has current flowing through it. So from this point here to this point here, we dropped 1 volt. From here to here, we dropped another 1 volt. From here to here, we dropped another 1 volt. We add that up, 1, 2, 3 volts. It equals our voltage gain. Hey, let's take a look at parallel circuits. And parallel circuits have branches. There is not just one path for the current to follow, but there can be multiple paths. So any current that leaves the battery here gets to, I'll refer to it as a decision point. It can either continue to travel straight, or it can choose to go through this light bulb. Okay. The total current in the current in the circuit is the sum of the individual branches. So in this case, we have 1 amp of current flowing through light bulb 1. It happens to be 1 amp in light bulb 2, 1 amp in light bulb 3. Our total voltage, 1, 2, 3 amps, is the amount of current leaving the battery. Okay. And then so we get to any one point here, the current arriving at that point has to equal the current leaving. We don't have a buildup of current at any one point. 3 amps arrive here, 3 amps must leave. In this case, 2 amps are traveling to the right, 1 travels down. That's known as Kirchhoff's law. Let's take a look at that. Hey, so all current arriving at a point, in this case, we got it right here. Our current arriving at this point is I1, has to leave through either I2 or I3. So I1 is equal to I2 plus I3. Let me back up for just a moment here. Hey, so something else that's important is that in a parallel circuit, all branches have the same voltage. There's a direct path back to the battery. So let's say in this circuit, because this branch here has 3 volts because I can trace right back to the battery. This branch has 3 volts as well as this branch has 3 volts. You saw that in your most recent lab. When you set up your circuit in parallel, the voltage across each of the light bulbs was exactly the same. Well, within a hundredth of a volt or so. Right? So that's an important thing. In a parallel circuit, the branches have the same voltage. They can have different currents. In a series circuit, the single branch has the same current, so all elements have the same amount of current passing through them. Hey, so now we can get to this point here. Hey, a nice little mnemonic that I use for remembering series and parallel. I think of the series like S like a snake. In a snake, let me back up there. Anything that snake eats here has only one way of passing through its system. It has to go in series. So the S is the way of me remembering series. Hey, and the other one, parallel, I remember the double L's. When I was in 3rd grade, I could never remember where to put the parallel or the double L in here until I learned what the word parallel meant. So I have the parallel L's in the middle of the word. So the parallel circuit provides, let's see, multiple paths. Hey, so in this next little section, I want you to define, imagine the circuit, or we'll have a circuit placed in front of you. Take a look at the circuit and then decide whether it's a parallel or series circuit. I'll pause for a few moments and then give you the answer. Hey, so our first circuit here, take a look at this. Is this a parallel or series circuit? Pause for a few moments. And you can likely see that there's only one way for the current to go through, so this is in fact a series circuit. Let's take a look at the next one. Take a look at this. Is this a series or a parallel circuit? Because you can spot these branch points. There's a branch right there. It gives our current a decision point. This is a parallel circuit. Let's take a look at the next one. Okay, so identify this as a series or a parallel circuit. As there's only one way for the current to go from this positive end of the battery through the light bulb, back through the switch, the negative end. This is a series circuit. Next up, let's take a look at this. Is this a series or parallel circuit? Hey, from the outlet, we go through the switch, in, out of the switch, in, out of the light bulb, back to the switch. There's only one path for the current to travel, so this is a series circuit. Let's take a look at this one. Again, we leave the battery through one light bulb, through the next light bulb, and back to the battery. This is, again, a series circuit. Let's take a look at our next one. Is this a series or a parallel circuit? Current leaves the positive end, and when it gets here, it can either go through the light bulb and back to the battery, or it can go to the next light bulb. Because there is a branch in there, this is a parallel circuit. Let's take a look at this one, series or parallel. Pause for a few moments. We have a battery here, different description of resistors, but because it has a branch point, it is a parallel circuit. How about this one? Series or parallel? And you probably guessed this one looks a lot like our most recent lab. From our positive end, we have to go through one light bulb, through the next, because only one path. This is a series circuit. This next one will look pretty familiar to you as well. Series or parallel circuit. Yep, we built almost this exact same circuit because there are branch points here. We know it is a parallel circuit. Hey, so let's go and we're going to do some calculations of voltage in and current in series and parallel circuits. Let's take a look at these. All right. Hey, again, to remind you that our resistance total for a series circuit is the sum of the individual resistances. In a parallel circuit, it gets a little bit trickier. Let's go take a look at this. We know that, hey, our resistance parallel, we're going to use Ohm's law. Remember, Ohm's law looks like this. V equals IR. There are many ways of expressing that. We could say that I, our current, is equal to voltage over resistance, or the last way we can do it, hey, is our resistance is equal to voltage over our current. So I've rewritten that. The resistance of this entire parallel circuit is equal to the voltage of the parallel circuit divided by our total current. Remember that Ohm's law applies to the circuit in general. This is Ohm's law here, the relation between voltage, current, and resistance. It applies to the entire circuit and every individual branch within that circuit as well. Let's take a look at this. Hey, so I have a 20-volt battery, okay, and I have it connected in parallel to a 5, 10, and 20 ohm resistors. Let's do the math. Hey, I know that current along this path is equal to our voltage, 20 volts, divided by 5 ohms. So going through here, I have 4 amps. Let's do this for the next part of the circuit. I is equal to 20 volts divided by 10 ohms. 20 divided by 10 is 2. We have 2 amps of current flowing through this branch. And this last part, I equals V over R. We have 20 volts divided by, we can see here, 20 ohms. And through this light bulb, I have 1 amp. So our total current, I total, is equal to 4 amps plus 2 amps plus 1 amps. 4 plus 2 is 6, plus 1 is 7 amps. So we know that there must be 7 amps leaving the battery, 7 amps returning to the battery. Let's take a look at what the equivalent, if you want the fancy word for it, the equivalent resistance of this parallel circuit is. So I have 20 volts divided by 7 amps. Let's put that in the calculator. And I get a value of something around 2.86 ohms. Hey, something about a parallel circuit is that the value of the overall resistance in a parallel circuit will always be less than the lowest parallel value. Right? If I were to take off all of this, I would still have 5 ohms. The other thing that's interesting is as I add more and more branches, that increases the current more and more, even if it's a very high resistance. If I were to add another circuit here, anytime I increase the current, I decrease the resistance. Important idea in a parallel circuit. One of the reasons why you have to have circuit breakers in your house, because your house is wired in parallel. If you put too many items on there, it can draw too much current and become dangerous. Hey, so let's look at some multiple choice questions based off of this. All right. Hey, so which circuit will have the greater resistance? I'll pause these briefly so you can figure it out and then let you answer it. So which circuit will have the greater resistance? Hey, we see that each of these are parallel circuits. There are more resistors on the right side. In fact, this side, 2 and 4, this has 6 ohms over here. This has 2 ohms, 2 ohms, 2 ohms. Each of these bulbs is 2 ohms. 4 ohms, 4 ohms, 4 ohms, 4 plus 4 plus 4, that's 12, plus 2 plus 2 plus 2, 18. 18 ohms. Which one has the greater resistance? Correct answer is B. Take a look at the next one. How much total resistance does circuit B have? I think we just answered that. It has it has 3 2 ohm bulbs and 3 4 ohm bulbs. Total resistance is 18 ohms. Let's take a look at the next question. All right. Which circuit will have the greater current? Make your selection. Hey, the correct answer here, of course, is going to be A, because remember, our current I is going to be equal to V over R. That's the same value of V in both of these cases, and because A has less resistance, it has more current. Hey, how much current will flow in circuit A? Let's take a look. Hey, we know that current is equal to voltage over resistance, 6 volts over 6 ohms. We know that it is 1 amp. Take a look at the next question. Hey, which bulbs will be individually brightest? The ones in circuit A or the ones in circuit B? Give you a few moments for this. Individually, the bulbs in circuit A will be brighter. Why? One, they have more current. Current is greater on each of these through the bulb, so therefore they will end up being brighter individually. They also have more voltage across each of them. Remember, we have to drop 6 volts, so we have to drop a certain amount of voltage here, a certain amount of voltage here. We only have 2 bulbs to do it, so each of these will have more voltage dropping across them. This one we have more bulbs with less current. Hey, so which circuit will have the greater total brightness or use the greatest amount of energy? Total brightness in circuit, which will be brighter, circuit A, circuit B, the same or cannot be determined. Hey, as you consider this one, think about what's going to make the room brighter. These 2 bulbs in circuit A hooked up to the 6-volt battery, or these 6 bulbs hooked up to the 6-volt battery. A hint on this, take a look at what the power involved in each of these is, all right? Take a few moments to answer this question. Pause it and we'll come back to it. The correct answer in this is circuit A, even though there were only 2 bulbs. Why? We have both greater current and greater voltage on each of the bulbs. And in fact, how much power does circuit A draw? We already know that the voltage in circuit A is 6 volts, and we determined earlier that the current is equal to 1 amp. 6 volts times 1 amp tells us that it is 6 watts. Hey, how much does circuit B handle? Let's take a look at that. Hey, circuit B, if you remember, had a resistance. Total resistance was 18 ohms. That's the sum of 2 plus 2 plus 2 plus 4 plus 4 plus 4. And we have 6 volts. So our current in circuit B is 6 volts divided by 18 ohms. We could simplify that to 1/3 of an amp. We could also say it's 0.33 amps. Let's go calculate that power. Hey, power is equal to voltage times our current. Let's take a look at this. 6 volts times 1/3 of an amp equals 2 watts. This 2 watts is much less than the 6 watts in our earlier circuit A. And let's take a look at a couple of problems involving parallel circuits, right? And I like to think of, why does a parallel circuit have less resistance? And I think of it as this way. For adding parallel paths is similar to adding more traffic lanes to a highway. Over here we can see on the right side we have something like 14 lanes of traffic, okay? So with maybe about the same amount of cars, the cars can move with much less resistance. Over here we only have, 2 lanes each direction, a total of 4 lanes. The traffic is much heavier. There's more resistance to the flow of traffic here. When we end up having less resistance in an electrical circuit, there's less resistance to the flow of electrical current as well. Right. Hey, and so as we just saw, we know that electrical power is our voltage times our current. Remember, voltage is the amount of energy per charge, and that our current is the amount of charge per time. So we put that all together, we could see that voltage times current is energy per time, which we looked at in the fitness center lab or topic challenge as our power, which is the change in energy per time. There. Let's go take a look at a couple of questions here. Hey, so we have a parallel circuit. So a circuit in parallel, we can see that we have a battery here. We said that there's a branch point right here, and it goes to 3 different switches, 3 different light bulbs. Our bottom switch is open. Hey, so when the lower switch is closed, what will happen to the upper 2 bulbs? And I want you to think about this. All right, will they become fainter, brighter, stay the same brightness, or cannot be determined? So go ahead and make your selection, and we'll check it out in just a few moments. The correct answer is stays the same brightness. When this is closed, the voltage on this bulb and this bulb stays the same. It just adds current, so then this bulb turns on, and actually the same brightness as the other 2 bulbs. Let's take a look at another question. Hey, how about the voltage in parallel circuits? When the lower switch is closed here, okay, the voltage from point A to B will be, so we're going to close this switch. Okay, we already know that this light bulb is going to turn on. We have an idea that these bulbs will stay the same brightness, so what do you think is going to happen to the voltage? So go ahead and answer that. We'll pause for a few moments. The correct answer is stay the same. From point A to point B, there's still a direct connection along a wire to the battery. There is no voltage drop along a wire because they have effectively no resistance. Hey, so let's take a look at this. Our current, our parallel circuits. Hey, assuming a 6-volt battery and each bulb has 12 ohms of resistance, the total current leaving the battery when the switch is closed will be blank amps. Go ahead and figure that out. Pause this for a few moments and we'll come back and calculate it. So calculate this on your own. A bit of a hint here if you haven't paused it yet. Hey, remember that Ohm's law applies for the entire circuit and for each element individually. We already know that, hey, the current going through this branch is equal to 6 volts divided by 12 ohms. I'll tell you that the current through this branch is 0.5 amps, similar to this branch as well. 0.5 amps. Take a few more moments and see if you can figure out what the total current leaving the battery is. Hey, coming on back now. So when this switch is closed, we know this bulb turns on. It will look just like the other 2. In fact, this will also have 0.5 amps flowing through it. So our total current leaving the battery is 0.5 amps plus 0.5 amps plus 0.5 amps. And if you calculate 1.5 amps, you are correct. Last thing we'll look at is resistance in a parallel circuit. Remember we said that as we add more and more resistors or parallel paths in a parallel circuit, the resistance drops. Well, we'll check it out. Hey, assuming a 6-volt battery and each bulb has 12 ohms of resistance, the resistance when the switch is closed between A and B will be, so we'll close this, light goes on. Now let's go back to that last problem, and I'll let you figure that out. I don't want to give it away too quickly. So how many ohms? Remember, Ohm's law applies for every item in the circuit and for the circuit in general. I'll give you another hint. R equals V over I. I'll pause for a few moments and have you figure this out. Hey, so welcome back. Hey, so we have 6 volts, and we know that our current from our previous slide when that was closed was 1.5 amps. 6 divided by 1.5 is 4 ohms. So only 1/3 as much as each of the individual bulbs. Hey, and our last question here, how about we'll take a look at the power in our parallel circuit. And here's our question. Assuming a 6-volt battery and each bulb has 12 ohms of resistance, sounds familiar, the total power in the circuit when the switch is closed will be blank watts. Okay, so we're going to close this. Light goes on. And we know that power is equal to current time voltage. Go ahead and pause this and see if you can figure this out. Hey, so welcome back. Let's see how you did. Okay, we could do this in total. We know that our current was 1.5 amps times 6 volts. 6 times 1.5 is 9 watts. The other way you could have done this was, hey, let's take a look at the power in each bulb. I'll say the power in one. Our current was 0.5 amps. Our voltage was 6 volts. You can see that, let's see, 6 times 0.5 is 3. 3 watts for each bulb. Now we'll go ahead and take that, multiply it by the 3 bulbs, and we also get 9 watts. So again, our power applies to the sum of the individual lights or for the circuit in general. And last note, just on parallel circuits, and household circuits are arranged in parallel. Why is that? Every time we apply or plug in an appliance, we always want the same type of voltage. Typically, household voltages are somewhere around 110 to 125 volts. Every time we want an appliance, our appliances are all designed for running in that range of voltage. If we had a series circuit, every time we plugged in another appliance, the voltage would keep dropping and dropping and dropping and getting lower and lower. So household circuits, as you can see here, a little more complicated setup is that one side is branched to, or let's see, one part of the circuit is branched to one side of the outlet. The other side of the circuit is branched to the other side of the outlet, so that no matter where we plug in, we always get the same amount of voltage. And for now, that's physics.